Hello. So, now we have to work together. It's not only me working. So, let's try to do some things together. So we'll try to also do some numbers. So the plan is the following: to look in the details how to write some codes for generating Gaussian vectors, translation vectors, then Bayesian analysis, and finally stochastic process to generate sample of stochastic processes. So I have some simple MATLAB functions here which I'm going to project. Oh, they are already there. And let's try to go through them to see if they make sense to you. And then we run some codes and look how they look and make comments. That is, you make comments. I'm going to do the picture and tell me what you see. But not, okay, this is a nice color. I need a bit more than that. Okay. So the first thing is a generation of Gaussian vectors. So you remember perhaps our notation. So X is a d-dimensional vector with this mean and variance. And we use the following representation. Mu is already defined. I'm using the same notation which we used earlier today. And G is standard Gaussian, independent variables. And I mentioned that this beta, it's a diagonal matrix. I'm sorry, it's a triangular matrix. And if you multiply one with the transpose, you get exactly gamma. But we don't have to do the work because MATLAB did it for us. So the code, it's really very simple to write. Now I see what you said if I need a pointer. But wait a second, I may work from here. Is up there? Yeah, okay, perfect. So let's go through this code, which is just an illustration of how it works. And as I mentioned, we are going to say the mean 0 because there's no reason to worry about the mean. Okay, but I think, guys, can you see where the pointer is?
Yeah. Yes.
So okay. I think it would be, thank you, but it would be easier for me to do it this way rather than, okay. So I just constructed a correlation function. So this is a correlation function I have constructed, and in this case it looks something like that. D is equal to 3, and gamma, I'm going to write, it's a symmetric matrix, everybody realize that it's symmetric, and in my case it looks something like this. This is a matrix. So this is a model basically as a first order Markov correlation type. And let me make a small diversion from it. Let's say this is a time series, and I need your help, really need your help right now. In which? So we start, it's running from I equal to 1 to whatever. So to start it, I need x0. And I have to tell you what W is. Right, so let's say x0 is Gaussian 0, 1. And W are independent. Again, Gaussian, 0, 1. And has nothing to do with x0. Right? So they are independent. So the jargon of this time series, if you've seen it before, this is the autoregressive series of order of 1. W is called the driving noise and so on. So let's calculate quickly the mean and correlation function for the series. But really, I want you to put the pencil down and to try it. Okay? So, expectation. I apply the expectation operator, right, on both sides of the equation. So it would be right? Linear operator, that is expectation of this plus expectation of W. Expectation of W is 0. So what's left? Right? Okay? So let's make some notations here. I call it the mean of time I. It can be temperature here, time a day I. It's equal to rho mu I minus 1. This is a recurrence formula. And we know that what's mu 0? 0. So what's the solution of this equation? Deterministic problem. Yes. Okay? Fine? All right. Correlation for log 1. That is, I want to find this correlation. Yeah, that would be a log 1 correlation. Because I'm looking at the time I minus 1 and I. The difference between I and I minus 1 is 1. So use formula. Instead of xi, main properties as expectation operator. That step is obvious for everybody? Okay. What is this? Not so fast. It's a mean, a variance, or what it is? It's a variance, right? Why I'm saying it's a variance? Because the mean is 0 everywhere, right? So it's a variance at time I minus 1. So let's call it this way. Variance at time I minus 1, right? Okay. What about this? Right. That's right. The answer is 0, but let's go step by step and understand why. W has nothing to do, X has nothing to do with Wi. But would not be true between Wi and Xi. Okay? Because Xi involves Wi, but not Xi minus 1. Because they are independent. because they are independent, we have, so this is by independence. This is 0. So what we find out is this rho. Okay. So we found the following thing, that the correlation between I and I minus 1, that is this correlation, I minus 1, it's equal to rho sigma I minus 1 squared. Okay. To go one step further, let's try to figure out what the variance is. What should I do to get the variance? We know the mean is 0 everywhere. I need to construct a recurrence formula for the variance. What if we have a formula for x? What if I square that, left and right, and take the average? I'm going to get the quantities I'm interested in. So let's try. So I take the equation and square it. That's a valid equality, right? And let's write it explicitly. Okay? I missed something? Plus what? Oh, here, yeah, I missed the square, thank you. Okay? So, let's look at this ends of the equation and write down what that means after I apply the expectation. So the expectation of this is, according to our notation, how should I call it? We call this, right? So sigma I squared. So we apply the expectation operator. It's equal to rho square sigma I square, right? That's the first term. What would be the second term? We looked at it before. It is 0, wasn't written up there? And Wi, expectation Wi square. 1. And again, what's the initial value? One. Okay? So, when I start from the very beginning, I equal to 1, what I get here? Rho square plus 1 for sigma 1, right? And keep going like this, and you can get the whole thing. So, why I got into this for 2 reasons. First, to practice a little bit with this correlation, just to reinforce what we did before, how to calculate, and to show you that the correlation for this type of autoregressive sequence decreases with rho. So this is what I use here. Log 1 correlation is rho. If you go to log 2, you are going to find this rho square. So this is how I construct the matrix. Okay. How can you find out if it's positive definite? What you can do right away, numerically. If I give you a matrix and I ask you, is it positive definite? What would be the eigenvalues? Calculate the eigenvalues. They have to be positive. Okay? All right. So this is what we constructed in here, right? I construct the upper part of this covariance matrix, and then I said they are symmetric, and I complete it. All right? And when we are going to run, we are going to have a list of these values. If you look at the input of this code, the entries are raw. This is the only thing I need to define for this example, right? The correlation function, the covariance function. If you need another covariance function, you just have to write it down and input it to the analysis. Okay, so up to here we did only this. We defined the covariance function for this particular problem. And now we begin the generation part. First, I think it's always useful to have a seed. And why I'm saying that if you don't, the computer is going to select it automatically. And if you want to reproduce that particular sample, you can't. When you specify a seed, you can reproduce a sample. So it's a very useful tool to have this thing. So this is all it does here. You're only going to start this seed, which I specify. This is just defined the length of the vector. And this will happen in a second. And then I just initialize this vector, which is going to collect all the samples of vector x. So in our case, this x is going to be something like this. Would be 3 in this direction, because it's a 3-dimensional vector. And in this direction is a number of samples, whatever number of samples we input. So coming back to the input of the problem, rho, which is our single parameter for the covariance. If that's not the case, you input directly the covariance. And S is the number of samples you are interested in. And then C is just for the generator to be able to produce against that particular sample. Okay, and now you call the MATLAB function. And by the way, I'm looking at this right now. The code is not really written efficiently at all, and I'll tell you why. Perhaps you already noted. First, I have to construct this triangular matrix beta. That is this beta, which has nothing to do with the samples. So I should depends only on this covariance matrix. So I should have done it outside the loop and store it. You see, this is a loop in which I generate samples, and I'm saying that this line, which gives a matrix beta, should have been before the loop, because I'm doing it repeatedly without any meaning. That, of course, is so fast it doesn't matter. But when it's a big problem, it does matter. So don't do it there. So I'm showing, don't do this wrong thing which your teacher did. So do it smarter before the loop. Okay, so now once you have it, all you have to do is to do this part. And this part is done this way. V is rand n that generate independent 0, 1 Gaussian variable, MATLAB function. And then you multiply beta, that matrix, with a particular sample, and keep doing this till you're done with the loop. And the rest is just plotting. I'm plotting dots of all the samples, and I'm going to show them to you right away. So is it clear how this code is done? Okay, including the correction that beta should have done before the loop. All right. So I'm going to do a couple of runs. First, this run. So it's a 3-dimensional vector, and I stay with 3-dimensional vector to be able to plot it. So if rho is positive, right? So the correlation is positive between this random variable. How you expect it? I'm going to show a cloud of points, right? 1 point per sample. How do you think this cloud is going to look in this 3-dimensional plot? So this would be coordinate 1, coordinate 2, coordinate 3. How do you think it's going to look, this cloud of points? What if it would have been 2-dimensional? If it would have been 2-dimensional, because it's easier to visualize. And rho is positive. How do you think the cloud of point would look? something like this. And depending on the value of rho, the cloud would be wider or narrower, right? If rho is almost 1, it would be almost like a straight line. What about if rho is negative? It's going to be the same thing in this direction, because it means large x1 means small x2 and so on. But something similar is going to happen in 3 dimensions. So it's F9, right? Okay, here you are. Can you see it? So this is for 0.7. So let's try right now higher correlation. Let's see 0.99. Yeah. So what if we make it really very small? Very weak correlation, right? Oops. Okay, so this is really almost independent, right? So it's like a shear. When you increase the correlation, they get more aligned on the main diagonal of x1, x2, x3. And when the correlation is almost perfect, they are essentially linear dependence. Okay. And if you do another, say a negative correlation, gain 0.7 negative, of course you have a very different, let's see if I can change them a bit. Here it's a bit interesting, since rho is negative, the correlation 1, 2 is negative, 1, 3, oops, so we have to see different things. So let's see, can I rotate it? I should be able to rotate it. Why doesn't let me? Oh, okay, now. Okay, this is 1, 2, negative correlation, and now I'm trying to do the other one. 1, 3. No, still 1, 2. How am I going to get 1, 3? I should be able to do it, right? Anybody help me with this?
Click and drag and then drag left.
It's so sensitive.
Yeah, keep going left, that'll be you in a second.
Okay, like this is good. No, this doesn't work. Oh, it's x2 is still there. That's a problem. Going more left. Okay, 1, 3 right now. No, I'm still getting this x2.
No, but that's off on your minor axis.
Anybody who can do that? Okay, if I cannot do it, you understand the gist of it. Okay, is nobody offers here? All right. All right, so that's basically the thing we have. Now, what if you want to translate this process, this vector? Let's suppose you want to generate something else. What you want x1 to be? Let's make something on x1. We want to make right now 2 samples of translation vector, right? So our x1, x2, and 3 are good because they are standard 0, 1, and they are dependent, right? So tell me what x translation 1 wants to be. Exponential. So let's figure it out. So you want x translation 1 to be exponential with this parameter lambda. Okay? That is a distribution f1 yeah, that's how it looks, this distribution for x positive. And this is uniform distribution. Or if you don't like uniform, we can make it Gaussian. And so let's try to see the algorithms and then we write it. How can we generate sample of it? Well, this is a natural logarithm. If I take this on the other side, it would be 1 minus u. It's equal to minus lambda x. Right, I apply the logarithm on both sides. That gives you where u, it's uniform in 0, 1. Right? So if I produce uniform 0, 1, I map it this way, I know it's exponential. But do you think this is true? That is, instead of saying is logarithm of 1 minus uniform, I say just logarithm of uniform because I'm really tired to write so much. It's the same thing because u and 1 minus u are both uniform. And if you go into translation mode, where g is Gaussian 0, 1. It's very clear to everybody that if g is normal 0, 1, phi of g is uniform 0, 1. But if you don't believe, you try it, right? That's all you do. You like the distribution and see it's happening this way. So what would be the algorithm then? x1, we have the magic formula right there. A minus 1 of the lambda logarithm at phi of our x1 from there, right? Our previous x1, which is Gaussian 0, 1. This is x1 we just produced, right? Which is Gaussian 0, 1. Okay. Now you may wonder how we do this. Well, it's not a big deal. Again, MATLAB comes to the rescue. And you take the sample, x1, I'm taking the sample which is still on the board, z samples, the first coordinate, and you do this function, CDF, normal. I'm going to write x1 for, but you know what it means, right? And indicate that the mean is 0 and the variance is 1. That does it. And of course, you have to do it, how many samples you have produced. So this is the first coordinate. The second coordinate, again, you have to choose a distribution and continue this way. So what I think would be extremely useful for you to take, can we make this code available? Yeah. To take this code and the samples generated, the Gaussian samples, and maps them in whatever distributions you want. So this is a homework, right? Which I'm not going to correct. But maybe what you could do, if you have problems, write in the website questions and we can interact. So select distribution of your choice, produce samples, and estimate the mean, the variance, and the distribution of this margin of distribution. And you are going to see that the correlation function in the Gaussian space and in the non-Gaussian space differ, but they are quite similar. Okay? And that the marginal distribution are as prescribed. I think it's a very useful exercise to do. Okay, any question on this? Because if not, I move to another code.
So this CDF subroutine there, function,
This one.
will generate, I mean, according to what you have written there,
Right.
will generate a uniform distribution for there. That will, are you pointing to the x1 there? I mean, that you are
This is
saying
x1 from there, right?
Okay.
Which is Gaussian.
That will be Gaussian, okay.
Right. So that's x1 from there.
Okay, and how can you actually put within MATLAB that you will actually generate a uniform function from that?
This is exactly how I'm doing. Because I already generated the Gaussian samples,
Yes.
which are there on the board. And when I do this, I'm doing this.
Ah, okay, fine.
So this is given by MATLAB. Otherwise, it would be a pain to do it.
Okay,
Right.
that's CDF.
That's a CDF, right. And MATLAB also has another function, ICDF, which inverts the distribution. And you have to put the name and all the parameters. Okay. Okay. Any other question on this code? So let's try to do something else. Bayesian analysis. And this is an input-output relationship, I consider. Y is the output. And I simplify significantly. X is the input. So that's the input. This is the output. Again, it's basically a very simple version of the simple example I presented originally. That is a displacement of the cantilever. Suppose that force is a constant and I scale it, the whole thing to be 1, so the displacement is the inverse of the stiffness. So x can be the stiffness and y is the displacement. Okay? So the setting is the following. X1 is a shifted exponential distribution. So let me draw a picture and write the formula for such a thing. You know, I have to shift it away from 0 because 0 stiffness, that means you have no beam. So that's ridiculous, right? So you have to make it a little bit more meaningful. So the PDF looks this way. 0, C, that's a shift. And the density looks something like this. lambda, why did I write x1 here? I don't know, by inertia. Should be just x. Okay. So what we are going to assume that we know that this is a functional form of the distribution, but we don't know the value of lambda. And you realize that value can be critical. So this is what we have here. Lambda is unknown. And we have some information. So the information is twofold, right? First, that distribution is exponential. That's a huge piece of information. So the information is x, it's exponential, and n independent samples of x. So let's call them x1 up to xn. So somebody went to laboratory, measured it, and figured out these numbers. We have such and such. So that's available information. Our objective is to find, for example, this probability. So, of course, if we know lambda, it's very easy to write it. But if we don't, we have to do something about it. So if lambda is known, so let me write it in parentheses here. If lambda known, this probability is simply the distribution, right? So the distribution would be 1 minus e to the minus lambda y critic, it's y critic minus c. That's provided that y critic is larger than c, as indicated before. But we don't know it. So from that information, first, we have to get a fix on this lambda. And the classical, there are several ways of doing. One, the frequentist approach would be estimate lambda somehow from this data, and then you get a number, and then plug it in, and of course you can construct some confidence intervals on it. Since we talk quite a bit of a Bayesian approach, I think I like to do it in a Bayesian setting. So let's see what would be the Bayesian framework for solution. First, we have to have some information on lambda, which is independent of experiments. So we need a prior information on lambda. Now, this, of course, is a source of huge debate. People who are against the Bayesian framework and people who are for it, or things like that. All I want to mention is that, particularly in problems which involve some physics, it is some ground to stand when we talk of the prior information. Because whatever you assume, it cannot violate the physics. And that provides some significant constraints. Of course, we don't have time to get in a debate on these things, so I'm going to use something very simple. I say that somehow, so-called experts told me that lambda is in this interval. It has to be positive because otherwise probability is not defined. And since I don't believe one expert more than the other, I'm going to say it's uniformly distributed in that interval. So our prior density on lambda, and I'm going to denote it by a prime, f prime of lambda, is going to be equal to, I think I use these, d2 my d minus d1 so I took a certain range, d1, d2, of course I have this condition. That is a bounded interval on the positive line. And of course, to be a distribution, the area has to be 1, so this I scale it this way. Okay. So this is prior to experiment based on physics and or other people who know better than us. Then the likelihood function. We construct the likelihood function. This, by the way, if you remember the base formula, we discussed it earlier this morning. This would be the probability, the analog of the probability of P of A, I, J, it was in that formula. So now I construct the likelihood function, which involves the results of the experiments, that is these conditional distributions. It usually is denoted and depends on data. Right? Once I give you data, you'll see right away, then I can calculate this probability. And it's simply, since values are independent of each other, it's a distribution of x, or the density of x, at xi. Xi, remember, are numbers, are measurements. So what this distribution is, we wrote it right here. Right, so with this distribution evaluated at xi. That is, this exponential with a lambda in front of minus lambda xi minus c.
So it shouldn't be the data given the parameter. The likelihood is that.
The likelihood is a function of the unknown parameter. The function is lambda, given the data. Right? I give you the data, then you have a functional form for the unknown parameter, which is lambda. So this I wrote it this way. If I change the data, it would be a different function. As you see here, xi's are numbers following an experiment. The only free parameter is lambda. So the likelihood is a function of the unknown parameter. Okay.
Okay. Yeah. Maybe it's just a notation because because you have the variable times the likelihood.
Right.
The likelihood is a probability of the data given the parameter.
Right,
You
but-
want to know which parameter.
Right, but you have to think of the meaning of likelihood. What it does, you have the fixed data, and then essentially you draw probability on the top of it, and you want to see how it varies when you change lambda. So this is the only moving part in that equation is lambda. The data is fixed. So this is why in more standard books of statistics, this is noted this way, lambda given the data. Because you change the data, you have a different function. But given the data, it's just one variation of lambda. Yeah.
That weight is just a function of the parameter, but it's not the density of the parameter, right?
No, it's not the density.
It's just a function.
Yeah, we didn't call it density. It's
you
a
can
likelihood.
express this as a density of the data given lambda as well. Because this
Well,
is
you can, but once you fix the data, it's no point to call it a function of data.
Yeah.
because they are fixed, the only moving part is lambda. So you emphasize the part which is moving. So in our setting, that would be, I think, lambda to the n, exponential, product of exponential going to sum, right? Minus, I think, lambda sum. Right? That would be the likelihood function. And now we have the posterior. So that would be the density. The posterior of lambda, you simply multiply the two prior and the likelihood, and you do some scaling to get it right, and that I'm going to just show the proportionality. And I call it with double lambda, this density. So it's proportional to whatever you said about prior times the likelihood. And you end up, and I said proportion because it has to be scale. I'm not showing the scaling here. So let's see what we have at this point. We start from a prior, which comes from somewhere. We discuss how. Given the data, we construct this function, which is called likelihood function. And then combining prior with the likelihood, you end up with a posterior. And that's your best guess on lambda. So usually if the model is right, makes sense, the prior may look something like this, and the posterior may look something like this, and somewhere here is a target. That is centered on the target. It doesn't mean that this happens all the time. If the model is totally wrong, that will not happen. Okay? So this is a sequence we try to do here. Now, one other thing, once you have this, you can address this problem. How you can address it? Well, in various ways. For example, what you wrote here is just a conditional reliability. That is, if I know lambda, the reliability will have this expression. Now, how can I decondition? Consider all the possibility of value of lambda and taking the expectation, nothing like that. Also, we can do confidence intervals, for example. And I'm going to show you solution numbers right away. So, estimate of this probability, I call it y. Okay. So we have this. Okay, so I'll stop. I'm not done. I stop just for a moment to make sure that you understand what I wrote here. If in a Bayesian framework, lambda, it's a random variable. Prior has this density, posterior has this density. So what I'm writing here, if I tell you lambda, you know how to write this. And it's written right here. Yeah? But if I want to get a Bayesian estimate of lambda, we do this. That is, you consider all posterior values of lambda and weight them with their probabilities. You can do something more. This is just an estimate, a point value. You can construct confidence intervals on it. Why? Because this is a random variable, right? So you can plot the distribution of this random variable, say, well, I want to be in this range. You have the density of lambda, you can calculate that. So that Bayesian attraction is twofolded in my mind. One, you can combine information other than data, like this, with data, and put it in a whole package. And then, particularly go to multidimensional problem, you can construct confidence intervals. In the frequency contest, in one dimension, it's easy to construct confidence intervals. When you go to higher dimension, it's getting really hard. Okay? So these are the important features of Bayesian analysis. And not to speak right now, of course, with a computer, all this MCMC, it's not a problem to go high dimension and to calculate the posterior densities. Okay, so here it's one example. I have to change the function. So Bayesian reliability. So let me go quickly through this analysis. X1 here, it's our X. Okay. So first part from here up to here is to generate samples. Instead of going to the laboratory, I went to MATLAB and I generated samples. So this is our data set. This piece here is the prior, which in our case, of course, when you take it uniform, doesn't make any difference because you have to scale it at the end. But the only difference that I say it's in this range, that is, I'm not going to look outside that range. Values outside that range are not allowed. And then it's a likelihood function. Now, of course, I wrote here the likelihood function. If you use it this way and you maximize it, it's really very bad numerically. So what is done, you take the log likelihood, and when you do the log likelihood, it's much nicer because here you have n times log of lambda. Here log is killing exponentially, it's much easier to work on it. So this is why I use that function. And let's see if I remember what I did next. Okay, so now I went back to the distribution. After I calculated, I went back to exponential through sync, and I put together the posterior PDF. And I scaled it to be a PDF. And then there are some figures which we are going to discuss right away. All right? So ready to run? Let's look at the input because I didn't specify the input. C and lambda are the parameter of the distribution which I'm using to generate. That's a true model. Right, I'm generating the data from here, and then I pretend I don't know anything about it. Okay. And then D1 and D2, of course, define the prior. And this is just for discretization I'm using. And Y critic, it's a vector. That is, I consider one, not just a single threshold, a sequence of thresholds, so I'll be able to do some plots against Y. And NS are the number of samples and again the seed. So let's run this. Okay, lots of plots. Let's go one by one. Okay, so that's the posterior density. Okay, in this case, I use 10 samples. Can you see where the arrow is? That's the number of samples. I use 10 samples. That is, n here is equal to 10. And this is the posterior density. If you look at the value of lambda, this is a true value of lambda I'm using for generating samples. So it looks pretty decent in the sense that the peak of this posterior distribution is very close to the true value. But of course, it's quite a bit of spread. the next figure, and let's try some other runs after this. Just to give you a sense, this, or rather, why don't we look at this? This conditional reliability for the range of lambda, consider in the analysis that is lambda according to the prior is between D1 and D2. So you see here a bunch of lines that are lined for different values of lambda in the range D1, D2. For each lambda you get a different curve. So it is quite a variation, which is reflected also in the posterior density. Because the posterior density is weighting these curves by different probabilities. What you see here, there are, of course, you can see perhaps just one line, which is a true reliability that is using the correct value of lambda. So that's a solid line. And the stars is this probability. So what's the story here? Well, on average, because it's an expectation of that random variable. That's a random variable. I wrote the expectation, a posterior expectation. So on average, we are doing just great, right on the top of it, right? But the enthusiasm is going to go down a little bit when you look to the variance. So that's the variance of that estimator, or the standard deviation rather, over y critic. So depending on the level of reliability, you can have significant variance, which is consistent with what you've seen in the previous figure here. Of course, when you are in this range, they are all the same because you cannot get there. When you are here, same story. But in between can be quite a bit, and of course the variance is reflected there. Now, let's try to do the same thing with more samples. Oops, no, I did the wrong thing. He told me what to do and I didn't do it right. Highlight and F9. All right. This is a posterior right now. If you remember the first one, I think it's obvious what happened. It's much narrower, and the peak is right there where it's supposed to be. And if we go to the variance, I think it was the fourth figure. It may look the same, but the ordinates are quite different. This is half of this. And if we want really to get somewhat in trouble, let's put just very few. Oops, again. I mean, in this case, even the mean is getting a little bit off. And that's the posterior. It's just completely off. So, I mean, the meaning is very clear. You can create information out of the blue just because you have a fancy mathematics. It just doesn't work that way. The only thing that mathematics does is to process efficiently the information, but will not create information. Okay? So one more code, if you still survive, and we're done. But before that, any question on this? Okay. So the last thing would be how to generate Gaussian processes. We discuss on the board, but let's try to do it So essentially what we are going to do to follow exactly what we wrote on the board before. The input is a spectral density, and this particular code is for the first order Markov process. You remember I give you a list of processes. One band limit is the second one, Markov. And the parameter of that was lambda. We assume that has unit variance. This omega 1 to omega left to omega right is the range of frequency I'm going to look at. In this particular case, I'm going to go from 0 up to a certain value. NH is a number of harmonics. In our representation, it was a sum k1 to n, this n, that's NH. Tn is the time interval we are using for representing the samples. That is, I'm interested in samples from 0 to Tn. And T is just a number of such time steps. And S, number of samples, and N seed, it's the sample, is the generation seed. Okay, so we start with the discretization part. First, we start this generator to make sure we did it and we're done with it. Okay. Now, d omega is a time interval or the frequency interval considered for discretization. So the right value of the frequency minus the left divided by the number of harmonics. And this is a vector selecting the frequencies, that these are the new cave if you look in our representations. And what is here is the calculation of sigma k square in the formulas. So we have all the ingredients right now to put the formula together. So the formula is written here. It's cosine and sine with A are Gaussian 0, 1, B Gaussian 0, 1, and the scaling factor is at sigmas. So that's the whole algorithm. Okay, so let's do a few samples. And in this particular case, lambda is 1, the frequency band from 0 to 5. We put 30 harmonics. We go up to 50 time intervals and just 5 samples to see how they look. And, oh, I didn't clear the other figures. And we have two pictures here. First are the 5 samples which we generated. And what you have here are estimates of the mean, the solid line, and standard deviation, the dashed line. The target is 0, 1. So any surprise that we are so much off, and it's quite a bit of fluctuation. What's the problem? Very few samples, right? So let's increase the sample size. To 100. Of course, you cannot see much in here. It's just a cloud of samples. But you can see quite a bit here. And what happened? Well, as you expected, the mean is getting closer and closer to 0, what it should be, and the standard deviation is getting closer and closer to 1. And from here, you can produce all kinds of translation models. For example, let's say if you want something else, instead of x, You want to do exponential of x, which would be a logarithmic function. Right? So let's plot just, and we conclude with this. Okay, so say x. The keys are located in a different place. So this one, just going, okay. How do I leave? Okay, finally I got it. X, and let's see, it's, okay, say 1. So the first 5 samples. Okay, so that, what am I doing here? Oh, I'm missing a. Okay, so these are just 5 samples. And now I'm going to translate this sample in something else. Oh, I have to do another figure first. Yeah, I mean figure. Okay. So these would be log normal samples. The Gaussian samples and the log normal samples. Okay. So of course you can produce any type of distribution in this mode, and it's trivial. Of course they are not the most general non-Gaussian processes, but is a certain class of a non-Gaussian process called translation. So I think I'll stop here, and if you have questions, let's talk. If not, yeah, question? Oh, okay. Oh, all right. That's good too.
Any question for now? Not the case, then let's thank Professor
Thank you.
Grigoriu.
Thank you.